So today's video is going to focus on our last learning target, which is interpreting and creating graphical models of motion. So the first thing I need you to do is to find your green unit organizer, and in slot 22, write position versus time, notes, and IP will be worth 10 points. And then find this page in your binder, label it 22A. So we've learned about graphing models of motion in our lab using a scientific model to predict speed, and now we're going to learn about one of the specific types of modeling motion, which is position versus time. So some basics we need to know is that position or distance goes on the y-axis, while time goes on the x. So if we have a graph, this is our y-axis, this is our x, distance is going to go here, and time is going to go here. If we draw a line, the slope of this line is going to be equal to the average velocity. So our formula for average velocity we know is velocity is equal to distance over time, which with a graph is going to be equal to y over x. There are four types of lines you're going to see frequently. So if we're moving at a constant rate, the slope is going to look like this. It's going to be a straight line. And to remind ourselves, we need to write if the slope moves away from the x-axis, the object is moving at a constant velocity. Now, what if the object's going really, really fast or really slow? If the slope looks like this, that means the object's moving very fast. But if the line if it's closer to the x-axis, it's moving pretty slow. So something we need to remind ourselves too is the more steep the line is, the more fast the object is moving. So say an object is speeding up, or in other words, it's accelerating. Our graph is going to take on the look of a smiley face like this. So it's starting off slow, it has a kind of a not steep slope, and it gets steeper and steeper and steeper until it looks kind of like a smiley face. So if the graph looks like a smiley face, then the object is accelerating or speeding up. Now say an object's slowing down. So it's going to start off with a steep slope because it's going faster, and it's going to get less steep. So instead of a smiley face, it kind of looks like a frown. So if the slope looks like a frown, then the object is decelerating or slowing down. Now, what would a graph look like if you're not moving? Well, if we're not moving, that means our position or distance isn't changing. So it'll be a flat line. So if the slope is equal to 0, then the object is not moving. Now before we move on, it's important to remember that these four rules and these four types of lines only apply to position versus time graphs. There will be a different set of rules for velocity versus time graphs, which we'll have to differentiate between much later. So if we're looking at a distance versus time graph, we need to be able to tell what's going on. So we're going to look at points A to B, then B to C, C to D, and D to E. So looking at points A to B, I see that the slope of the line is really steep. So right now we're looking at this line right here. So from A to B, it's a straight line, so that means I'm moving at a constant velocity. And because it's pretty steep, I'm moving fairly quick. So I'm going to put constant velocity and fast. From B to C, I see that it's a flat line. So knowing that it's a flat line, I know I'm not moving. My position isn't changing. From C to D, it's a straight line again, which means I have a constant velocity. But it's not as steep as A to B. So that means I'm moving slower. And then from D to E, it's a flat line. So that means I'm not moving again. Now, it's possible using a distance versus time graph to solve for how fast we're actually going. So we're able to do some math looking at a graph, and it's all about solving for slope. So I'm going to do a quick review on how to solve for slope. Now in algebra or CMP, you should have learned that the slope of a line, which is m, is equal to the change in y over the change in x positions, or the second y coordinate minus the first y coordinate over the second x coordinate minus the first x coordinate. In order to relate that to our distance versus time graph, we need to remember that our y value is our distance and our x value is our time. So let's look at this distance versus time graph down here. So our first point is 3, 5. Remember that coordinates go x and y. So we're always going to go left to right. So this is going to be our second x coordinate, xy coordinate. So this will be x2, y2. Well, this will be our first xy coordinates. So let's try to plug these into the equation we have above. So if we have x2, y2, and x1, y1, we need to figure out our y2 unit. So that's going to be 8 minus, let's go to y1, we need to go back down here, 5, over, and now we need to do x2, so x2 is going to be 10, minus x1, so down here it's 3. So 8 minus 5 is 3, while 10 minus 3 is 7. So our slope is 3 over 7. Now because it's a distance over time graph, 3 over 7 is our slope, which means it's actually our velocity too. So if we're solving for our average velocity, it would be 3 over 7 meters per second. Now let's do that on a bigger graph. So we're going to calculate the speed from A to B, B to C, C to D, and D to E. So let's write a little reminder to ourselves up here that slope is equal to y2 minus y1 over x2 minus x1. Let's solve from A to B first. So we're solving this line right here. Remember, we go left to right, so our first coordinate is going to be A, our second coordinate is going to be B. So if we need to find y2, and I know coordinates are in x, y, 3, this 3 right here is going to be my y2 coordinate. It's going to be 3 minus 0, because that's my y coordinate down here, over 2, it's my first x coordinate, minus 0, because that's my first x coordinate. So 3 minus 0 over 2 minus 0 is 3 over 2. Let's put that into a decimal, so 1.5. But we're not done. Because it's a distance versus time graph, our slope is equal to our average velocity, which is meters per second. Now let's solve from B to C. So if we're going from B to C, this is my first x coordinate now, this is my second. So my second y coordinate, or y2, is going to be 3 Well, my first y coordinate is also going to be 3. Now my second x coordinate is going to be 4, while my first x coordinate is going to be 2. Now, I'm sure you could tell it's already a flat line, so you're probably saying, well, it's a flat line, it's not moving. That's true, but we need to prove it mathematically. 3 minus 3 is 0 over 2. This will equal 0 meters per second. It's okay if you're saying it's a flat line at 0, but I just wanted to show you how it is mathematically as well. Now going from C to D, we are going to say, okay, well our second y coordinate is 5, our first y coordinate is 3, over 8 minus 4. So 5 minus 3 is 2, 8 minus 4 is 4, so it'll equal 0.5 or 1/2 meters per second. So even looking at the slopes, this is much steeper than this. We're going from a slope of 1.5 meters per second to 0.5 meters per second. Now let's look at D and E. Our second y coordinate is 5, and our first y coordinate is 5 as well, because it's a flat line, so they're all on the same y coordinates. And our second x coordinate is 13, minus our first x coordinate, which is 8. So 0 over 5 is still equal to 0 meters per second. So again, it's a flat line, the slope is equal to 0, so that means our object's not moving.